Let's continue our discussion about integer programming formulation. The last example that we saw in the previous lecture was a fixed cost example, and now I want to introduce another case of integer programming formulation, which is also very popular and is known as either or case. So let me write it down. Still IP formulation, and we will discuss the case of either or. I would like to start this topic with a general discussion. Suppose that I have an optimization problem, maximize a linear function C transpose X. I'm in a two-dimensional space. The vector of variables has two components, x1 and x2, subject to vector x belongs to set which I denote by capital X. Okay? A general optimization problem. And what I know is that this set capital X, the set of feasible solutions, has a shape like this. Okay, you already know that this shape, this is the set capital X, this is not a convex set. So it is impossible to have a linear program whose feasible region is like this shape, which means that we cannot cast this problem as a linear program for sure. Okay, but either way, we want to solve it. So what can we do? Let's be a little bit creative. Okay, we can say I want to consider every point in this region, but I don't have to consider them all at once. I can divide this region into two convex regions like this. Let's call the set of points in this region A and a set of points in this region B. Then this set, the original feasible set capital X, is the union of every point in A and every point in B. Now A and B separately are convex sets defined by some lines, so we can actually, if we just want to consider every point in A, we can cast it as a linear program. Also, if we just want to consider the points in B, we can cast it as another linear program, right? So we can actually solve this problem in two steps. First, we can solve max C transpose X subject to X belongs to set A. Let's assume that it gives us an optimal solution X star and optimal value Z star. Then I will solve another problem with the same objective, but now I just consider the points in set B, and suppose that it gives me an optimal solution X tilde, an optimal value Z tilde. Then I can easily compare the value of Z star and Z tilde, because I know that X star is the best point in A and X tilde is the best point in B. So I just need to choose the best between X star and X tilde. Okay? So instead of formulating one problem, I could actually formulate it as two different linear programming problems. Okay? Still not good enough, because my objective is to formulate a single program, a single mathematical optimization formulation for this problem, not two of them. But it is still progress, because it shows me that if I can define a switch to include in my optimization problem, then I can actually solve it, right? I just need an embedded switch in my formulation that switches between these two problems. These two problems have the same objective value, but they consider different set of feasible solutions, right? In order to make it more clear, let me go forward and let's say, for example, I know that region A is defined by a set of linear constraints, something like 2x1 minus 3x2 greater than or equal 5, something like 5x1 plus x2 less than or equal 10. So I actually know the defining constraint of these two sets. Some constraints like this. Now, as I said, what I want to do, I want to incorporate a switch into my formulation. And that switch is nothing but a binary variable, okay? By a binary variable, I want a binary variable, and that binary variable will act like a switch, right? Because a binary variable takes on values 0 and 1, okay? And if I introduce a variable like y, which takes on two values 0 and 1, I can use those values to switch between these two problems. The point is, here I have two set of defining constraints, set that defines the set A and a set of constraints that define the set B, but I cannot use them simultaneously, right? That's the point. The constraint defining A acts simultaneously and define this region. The constraints in here define region B, they act simultaneously. In fact, B is the intersection of the feasible half spaces defined by these constraints, and A is the intersection of the feasible half spaces defined by these constraints. But the relation that exists between them is an OR relationship. Remember that these constraints, the constraint that define A, the relation between them is an AND relationship. For example, you say 2x1 minus 3x2 is greater than 5, and simultaneously 5x1 plus x2 less than or equal 10. All of them must be simultaneously satisfied by one point, by one feasible point. Okay, the same with B. But between A and B, between these two sets of constraints, there is an OR relationship. Okay, my optimal solution is in A or in B. By implementing this OR, I will consider every point in A or B. In other words, every point in A union B. Okay? Now, let me introduce you the technique that we use to use as a binary variable as a switch. Let's focus on the constraint defining the set A. 2x1 minus 3. x2 greater than or equal 5. I add this term in here. Now let's see what is the effect of the change that I made. Okay? We know that the value of y can be 1 or 0. If the value of y is 0, then this term and this term will disappear. Then I will have the original constraint that I have for set A. Okay? But if y is 1, then what I will have here, okay, I have to add that m is a very big number.
It's very, very big.
Very, very big. Bigger than any value that x1 and x2 can get. Bigger than any value that a term involving x1 or x2 can get. Very big number, okay?
It's very, very big.
So if y is equal 1, then I will have 2x1 minus 3x2 plus very big number greater than or equal 5. You see that the effect of 2x1 or 3x2 is actually negligible compared to the big number m. So at the end, regardless of the actual value of x1 and x2, if the value of y is 1, I will have some very big number greater than 5, which is trivially valid. Okay? So this if y is 1, this constraint is trivially satisfied. Let's look at the second one. 5x1 plus x2 less than or equal 10. If the value of y is 1, then I will have 5x1 plus x2 less than or equal 10 plus very, very big number, which is still very, very big number. So this constraint becomes a combination of x1 and x2 be less than or equal some very, very big number. Okay? If the value of m is big enough, this constraint becomes redundant as well. Okay, so if the value of m is big enough, with the choice of y equals 0, I will get original a constraints, and if the value of y is 1, this constraint becomes redundant. Okay, this is actually what we want, right? This is a switch. If my switch is on 0, I'm considering this set of variables, this set of constraint, this set of constraint. So if the value of y is 0, it means that I am considering the points in set A. If the value of y is 1, I'm not these constraints all becomes redundant. Now I have to do the same thing with the same switch. Remember, with the same switch, I have to do the same to set B. Y is a binary variable and m is a very big number. Now I want to do the same with the same switch. I want to have a similar effect, but with a different value of y. x1 plus x2. I want that, this is what I want. If y is 0, I want this set of constraints to become redundant. And if y is 1, I want this set of constraints to be in effect. So in this case, my switch will work perfectly. If y is 0, then I will have this set of constraints and ignore this set of constraints completely. Alternatively, if the value of y is 1, I will consider this set of constraints and ignore this one completely, right? Now note that the effect of y here is the opposite of the effect of y in the other problem. In other words, in the other problem, in the first part on set A, I used my. Now I have to use m times 1 minus y to get the same effect, okay, because it is the same switch. So in order to make this what I want, I will multiply the left hand side with this greater than or equal 5, and see that if the value of y is 0, then I will have 1 minus 0 is 1 times m becomes m. Then I will have in the left hand side, I will have a very big number greater than or equal 5. I guess it was 10. Sorry. Greater than or equal 10. And do the same, and if the value of y is 1, this term completely disappears and I will get the original constraint. Less than or equal 6 plus m times 1 minus y. Again, if the value of y is 0, I will have some combination of x1 and x2 less than or equal a very big number, which is a redundant constraint as we want it. And if the value of y is 1, then I will have the original constraint. So you see, by altering the constraint that I have, remember, I couldn't use the original constraints defining set A and set B simultaneously in a single linear program, but by introducing a binary variable y and a very big parameter, a very big number m, I could incorporate this switch into my formulation. Now I can put all these constraints together. Okay, so I can write a single integer program like max C transpose X subject to 2x1 minus 3x2 plus my greater than or equal 5, 5x1 plus x2 equal 10 plus my, and from this side x1 plus x2 plus m1 minus y. Note that still every function here is a linear function. You can easily expand the corresponding terms in here and bring every variable to the left hand side. So it is a very nice looking problem. And x, they were supposed to be non-negative, they are non-negative, and what we did was to introduce a new variable, new binary variable xy. Now I could do that. I could implement a switch into my problem. So instead of formulating two different problems, I could cast my problem into a single integer programming problem. Okay? Now let's see some examples how we can use this technique to formulate some real-world problems.
I'll be back.